Welcome back to another HVAC Engineering Techie training video. Today's video is on constant volume air handling unit systems. So today we're going to cover all the different systems that are constant volume for air handling units. And in these videos, we talk about the system itself, how it's made up, what it is comprised of, and we talk about how it's programmed and how it's operated. So you kind of understand how this all goes together. And we talk about the sequence of control for these units. So remember that the HVAC Engineering-Techie is all about talking about everything HVAC: engineering design, construction, equipment, systems, test and balance, controls, efficiency, and performance. So a lot of different subject matter. Today it's about air handling units. Please do me a favor and become a subscriber. Join our technical group. We're all trying to learn more about HVAC as we go. So please become a subscriber. That helps me out a lot. Hit the thumbs up if you would. Those cost you nothing. They're absolutely free, but they do a lot for me, so I would appreciate it. All right, let's get started on air handler constant volume systems. Okay, so now we're going to start with basic heating, ventilating, a two-pipe draw-through arrangement, which these are normally what we call heating ventilating units. So they're basically heating units. They have a fan, a heating coil, and a filter system. And of course, they just draw the air in and heat it and push it out to the space. These are normally used in non-occupied spaces, but full-time occupied spaces such as garages, warehouses, that sort of thing. They're two-pipe because they only have two pipes. They only have one coil. That's the definition of a two-pipe system. Pretty simple, huh? And then we normally have some kind of control system. The control system usually is a fan starter, stop the fan, a current switch to tell when it's on or off, a valve. It could be a three-way, it could be a two-way. All kinds of arrangements could be here. And then we have a room sensor. And the controller controls the basic operation of the unit. And the sequence is really simple. The sequence is the fan should be on when the schedule is in the occupied mode. Open and close the control valve to maintain the room temperature. Now, this one here is a two-position valve. It could be modulating, depending how big the unit is, but the smaller ones are normally just two positions. So they turn it on for a while and turn it off. It has no outside air. It's just a heating unit for the system. So that's the basic system of a heating ventilating unit. Really simple. Okay, now let's look at a basic two-pipe fan coil unit. It's a blow-through arrangement, normally under 2,000 CFM. It can be larger, but normally these are small fan coils for small spaces. And these units have a filter system, a blower, a cooling coil, and may have an electric heater if it needs heat. If it's cooling only, it'll just have a cooling coil. And it can have an outside air intake, which will have a damper on it to be able to modulate or operate between unoccupied and occupied. And the way this works, this has, of course, it's another two-pipe unit. Now this one here you see, it doesn't have a three-way, it has a two-way valve, and that's just part of the design of the system. And this can also be two-way, or it could be a modulating, you never know. So then it'll have a control system, and this control system is very similar to the other one. It'll have a starter for the fan, and the reason this doesn't have a VFD is because this is a constant volume unit. It runs the same all the time. It'll have a current switch to tell it when it's running or not. And then it'll have this damper actuator. And the reason that's there is when this unit's off, this is to be closed. So we don't get outside air infiltration into the building when the unit's off. Then, of course, this one has a chill water a valve over here that's run by this controller. And then we have, in this one, we have heats. We have an electric strip heater here. And we also have a discharge temperature sensor to be able to monitor the supply air temperature. And then we have a room sensor, temperature sensor. Now normally this particular supply air temperature sensor is the cheapest and most effective system monitoring point you can have, because it'll tell you if this system is supposed to be in the cooling mode. This sensor will tell you if it did that or not. You know, if it's supposed to have 55 degree air and it's got 75 degree air, there's something wrong with the unit. So that's a point to tell you if the system's working or not. Or if it's supposed to be in the heating mode, it'll detect the duct temperature and tell you if the strip heater is working or not. So this is a very low cost, very effective monitoring point for the system. Now its sequence is also very simple. The unit shall be on and the outside air damper open when the schedule is in the occupied mode. Now this system is balanced, so when it's in the open it gets the correct amount of air. Now remember, these are constant volumes, so it's always the same amount of air running through the air handler. And we balance the actuator, and we do that by setting the stop. So we'll set the stop on the damper so it can't go beyond the point we want it to. It'll go shut when it's off and go to that point when it's on. Modulate the control valve and stage the heat strip to maintain the room temperature set point. Monitor the supply air temperature and fan status. Now, these sequences I'm showing you here, these are simple sequences. These are not to be construed as a programmer sequence. And these are normally the sequences you would see on the drawing from the design engineer. He's trying to tell you what he wants it to do, not exactly how he's going to get it to do that. So that's the programmer's job. So when you take the control system module, if you take that, when we go over programming sequences, they'll be much more detailed. They'll have exit points, entrance points. They'll have timers. They'll have a lot of different things that the programmer needs to put in here to actually get it to work correctly. But these sequences are simple, high-level sequences intended to tell you how the system works, similar to what you'll find on the drawings. Now we have a 4-pipe fan coil unit. Again, this might be 2,000 CFM or less, might be a little bit larger because it can also have 4-pipe air handlers, which we'll talk about in a little bit. But this is simply a fan coil unit. Most fan coil units are blow-through. In other words, they take in air through the blower and then through the coils, so they're blowing through the coils instead of sucking through the coils. So remember, this is in a positive discharge place, a location of the air handler. So these condensate drain traps need to be designed for positive pressure, not negative pressure. So now this one has a cooling coil. It's 2 pipes coming in, and then we have a heating coil. That's 2 pipes, and that's why it's called a 4-pipe. However, you need to make one thing. Just a 4-pipe has a minimum of 4 pipes. We could have up to 3 or 4 coils, so it may be 8 pipes, but you don't call it an 8-pipe. 4-pipe is more than 2. So then the control system on this one would be similar to the others. Again, it's constant volume, so the fan is start-stop to the starter, has a current switch for status. We have an outside air damper again, the same thing as the other unit, but it's balanced. When it's open, it's at the right airflow for outside air, and when it's off, it's off. And then we have a chill water valve, and then we have a hot water valve. And again, we have that supply sensor point for a monitoring point. It's a supply duct temperature sensor. Again, the sequence is on this. The fan shall be on and the outside air damper is in the occupied mode. Modulate the control valve to maintain room temperature and set point. Monitor supply air temperature and fan status. Sometimes it's hard for me to read these because on my production screen they're really, really small. Anyway, I'll get to it. You can read it better than I can. Okay, now here we have a 2-pipe constant volume air handling unit. Now you can see this looks different because it's a larger unit. These could be really large sometimes. And this particular one has a supply fan and a return fan and an economizer section, which we'll get into describe here in a second, and filters. Now this is a draw-through arrangement where when we also have coils. Here's a cooling coil. We also have a heat strip on this one. So this is a draw-through unit with a full economizer that has a return fan, return damper, relief damper, inlet, outside air damper, filters, and normally we have a pre-filter and a final filter. Pre-filters are designed to catch most of the stuff so it doesn't get into the final filters. And the reason for that, these are a lot more expensive than these. So we want to make these last as long as we can. Normally we change these pre-filters every quarter, every 3 months, and we try to make these last at least a year, and sometimes it may last longer. Now what's a little bit different, because this is a constant volume unit, remember, we're still talking constant volume, so fans are constant volume, so the airflow volume does not change. We have a coil here for the chill water coil. Now again, remember, when you take the system for chill water, you'll notice a lot more, but But one of the most important things on these is that the supply water, which is this one right here, always enters at the leaving side of the coil. That's really, really important. If you do it the other way around, where you have the coldest water coming in over here, then when the air leaves this coil, it's going to be at the return water temperature, which is going to be, it could be 65, 70 degrees. It could be warmer. And the problem is that doesn't allow the cooling coil to properly dehumidify the air. It doesn't take the moisture out of the air. So you'll get higher temps in the space and problematic. So they always must be leaving. A supply needs to enter on the leaving side of the coil. Really important. And we have a supply fan that's constant volume. And on this one, we have a strip heater. And again, we have that monitoring point, supply air temperature sensor. We have a room sensor. In this case, this room sensor is a temperature and humidity sensor in one unit, so we can tell what's going on in the space. And of course, we have a motor starter and a current switch for each fan and a controller. These are normally slightly larger controller than the others. Still the same thing. So now let's look at the sequence. Okay. The supply and return fan shall run anytime the system is in the occupied mode and the outside damper will be open to the minimum position. And remember this is constant volume. That outside air is balanced to the correct position. So now it's a little more difficult here because remember, these are economizer dampers. So this damper now, instead of like the previous ones, which were closed and open to a balanced position, this one has 3 positions. Closed for when it's unoccupied, open to the balanced position, and then full open. It has 3 positions. So that's a little bit different than the others, and we'll get into why that's that way in a minute here. So modulate then the chill water valve, and this is a modulating valve. It's not 2-position, but modulating. And remember, the valves are always on the return pipe. And the reason for that is if you put it on the supply pipe, there's many guys argue that that's okay. It's not okay. And the reason is because it can cause air to separate from the water because of the way it's a throttling device. And when it does that, because it's changing pressures, you have on the supply side, you have higher pressure coming in, and then it closes, it gets lower pressure. Well, that can actually expose air, and you can't airlock a coil. So and then also there's also coil authority, which we'll get into that later in a hydronic video. But remember, all control valves need to be on the leaving side of the coil. Okay, so we have the valve. It modulate the chill water valve to maintain the room temperature set point for cooling. If the outside air temperature is between 45 and 70 and the outside air temperature is 10 degrees below the return air temperature, enter economizer mode and modulate the outside air relief and return air dampers to maintain the room temperature set point. If the room temperature rises more than 2 degrees above the return set point, go back to the normal operating mode. So this is the economizer mode. Now these numbers in here are arbitrary and they have to be modified for the region you're in. If you're in a real warm region, those might be okay. They're really cold, you may have to change those slightly, but this is the basic method of doing a dry bubble economizer. These are dry bubble economizers since it doesn't have anything but it has a return temperature. So I forgot to mention that. These are just temperature sensors. We don't know what the enthalpy is, so we can't be using an enthalpy economizer. This is a dry bubble economizer. Monitor the room temperature, supply temperature, the room temperature, supply air temperature, supply and return air fan status, and of course you can monitor return air temperature. Okay, so that's the basic senses of a 2-pipe constant volume air handling unit. Okay, so now this is a 4-pipe constant volume air handling unit. And you see this is similar to the other unit. There's a supply fan, return fan, economizer, dampers, filters, and a cooling coil. And on this one, since it's a 4-pipe, it has 2-pipe on the cooling coil, has 2-pipe on the heating coil, and it has 2-pipe on a preheat coil. So, like I said before, the definition of 4-pipe is a minimum of 4-pipe. This one actually has 6 pipes, still called a 4-pipe unit. So this is designed to preheat the air. So if we have cold air, there's a cold climate, that the incoming air can actually be way too cold. Then we preheat it up with this one. This is the cooling coil, and this is the heating coil. So our control system is similar to the other one we had. We have motor starter and a current switch on the return fan, a motor starter and a current switch on the supply fan. We have a controller, of course. We have a room temperature sensor and humidity sensor in one unit. We have a supply air temperature sensor. We have a return air temperature sensor, and we have a mixed air temperature sensor at the cooling coil. This is a temperature sensor at the leaving position of the cooling coil. And then, of course, we have a modulating valve for the preheater, a modulating valve for the cooling coil, and a modulating valve for the heating coil. And that's the control points we have. And, of course, we have the dampers, actuators for the return damper, the outside air relief damper, and the outside air intake damper. And now the sequence of controls. The supply and return fan shall run and the outside air damper shall be minimum position anytime the system is in the occupied mode. So remember, this outside air damper is going to be closed when we're unoccupied. When we're occupied, it opens to the minimum outside air requirement because that's constant volume. And then when we're economizer, it's modulating between that minimum position and full open to maintain this room temperature. So modulate the preheat hot water valve to maintain the preheat set point temperature of 45 degrees. Measured at the leaving side of the cooling coil. Modulate the hot water valve to maintain the preheat set point temperature of 45 degrees. If the cooling coil outlet temperature drops below 38 degrees, stop the fans, close the relief and outside air dampers, and open the return air and chill water coil valve 100% and send a freeze alarm. So this preheat coil is designed to preheat this air coming in. And because the cooling coil set point is normally 55 or higher, then this temperature sensor can be used to also run this valve, this coil, because we want it to heat air up to a minimum 45 degrees, not over that. So as the air comes in colder, it's going to hit this hot water coil and preheat up to 45 degrees. It goes through the cooling coil, and that may be, more than enough to do it, or it may actually not do anything and let it go to this heating coil, and the heating coil raises on up to where we want the supply air temperature. So these preheat coils are designed for areas that have very low temperature, and it does two things. Not only does it preheat the air and it keeps things from freezing up, it also helps this heating coil. So this heating coil doesn't need to be quite as big because it got one here. You do have to be careful that you don't freeze this coil up, so it has to have the right velocity and the right conditions in the coil to not freeze the actual coil up. So if we have pre-freeze coming in here, 30-degree air or something, this has to be big enough and have enough hot water in it to not allow that coil to freeze. Modulate the chill water valve and the hot water valve on the heating coil to maintain the room temperature set point. If the outside air temp is between 40 and 70 degrees and the outside air temperature is 10 degrees below the return air temperature, enter economizer mode and modulate the outside air relief air dampers to maintain the room temperature set point. The room temperature rises more than 2 degrees above set point, return to normal operation mode. Okay, so remember, constant volume. So it's constant volume. So when the outside air temperature is cold enough to be able to do the cooling load, then we'll enter economizer mode. And in economizer mode, we basically open the outside air, bring the outside air in, and the return fan then sucks air out of the room and then delivers it to the relief damper. Now we want to use this for temperature, so we're going to modulate these such that we maintain room temperature. Now, one of the jobs of a return fan is to maintain building pressure. If you didn't have a return fan and you went to economizer mode, it's going to bring in this outside air, and it's going to pressurize this room to push it through this system if you didn't have a return fan. And people don't like that because what happens, it ends up overcoming the door closers and pushes the doors open. So the return fan is supposed to run such that it never allows us to get over. Now, you can do this two ways. A return fan can be, if it's variable volume, it can speed up and slow down to do that. But since it's a constant volume, we have to rely on the dampers. So basically then what we do is we make sure this damper and this damper are modulating opposite of each other, and this damper is modulating for that temperature. So they can modulate all together to maintain the same room pressure and still use this for temperature, because we're really not changing the room flow. We're only changing its temperatures by mixing air between this return damper and this outside air damper. So in this one, these all three would be tied together, that this one and this one would track, and this one would also track to your original balance condition. So these are a little tricky to set up, but they can be set up correctly. All right, now we have a room sensor here. Remember, that's got a humidity sensor in it. So if the room humidity rises above 60%, place the cooling coil into dehumidification mode. When the room humidity drops below 45%, return the normal temperature control mode. In dehumidification mode, modulate the chill water valve to maintain the cooling coil cooling deck, leaving temperature to maintain 50-degree room humidity, and modulate the hot water valve to maintain the room temperature. Now, some people don't like this sequence because they've been bitten by freezing up a coil, or worse, not being able to adequately control the humidity. But what the thing is here is that, remember, this coil is going to get real cold. So to do this, when we go into mode, we're going to drop this cooling coil down to normally full open. And we're going to get this air as cold as we possibly can to drop the humidity out of it. Then we're going to reheat it back up so we don't freeze the people up. That's why in a job where you want to dehumidify, the heating coil must be downstream of the cooling coil, because otherwise you're going to freeze the people. Now, because this coil is there, we're reheating it down here. That is an energy problem. If we cool the air all the way down to as cold as it'll go, maybe it'll go to 48 degrees, and then we're going to heat it all the way back up so we don't freeze the people. That's okay as long as we need it. But if we don't need it, there's no reason to do that. So my sequence here is basically to say we're going to, the room's at 60% humidity. We're going to turn this thing on full until it gets down to 50%. And then we're going to modulate this cooling coil to maintain the 50% humidity in the space. And then as the issues with whatever caused the humidity goes away and it drops to 45%, then we're going to stop this mode and go back to normal heating mode. This will actually do the best of both worlds. It will drop the humidity and it'll save some energy. So I like this sequence better because it doesn't matter how high humidity condition you're in, this sequence will operate. Now, you can change these set points percentages. You could have it modulating to 48% or 50% or 54%. It's depending how you want to run the system. Monitor the room temperatures, supply air temperature, and supply air and return air fan status. So that's a 4-pipe constant volume air handling unit. Now we'll get into the more exotic systems. This is a constant volume dual duct air handling unit. And these air handling units were originally created to provide heating and cooling to a space with zone control. So, originally we had the 4-pipe air handling unit, and we didn't have any zone control, so we just one great big zone, and you maybe use some reheat coils out there to try to change the temperature of the zone. Well, this was our first attempt at how to make a VAV system without a VAV system. And this is called a dual deck unit. And the reason it's called that, it's got you remember this previous unit was a draw-through unit. This is a blow-through unit. It has a supply fan that blows through a cold deck and a hot deck. So this one has a cooling coil, and then it has a hot water coil on top of it. And this is a hot deck, and this is a cold deck. And the reason for that is this has a hot water coil and a chill water coil. And it has 2 ducts. So it runs 2 ducts throughout the space. It has a cold duct and it has a hot duct. And at the end, out at the spaces, they have 2 VAV boxes that actually modulate between the cold deck and the hot deck to supply the right room temperature. Now, in the beginning, these were pneumatic, and these were actually had one pneumatic actuator, and the dampers were attached to the same shaft. So if the cooling valve was open, the heating valve was closed. Heating valve was open, the cooling valve was closed, or anywhere in between, it was proportional. And these work really, really well. So the dual variable box is controlled by downstream flow. Now, nowadays, in a modern system, in a VAV system, it's not a VAV course, but VAV system, we put a pitot port here, a ring, pitot ring, and it maintains this damper as reset by the room sensor. So these sensors are up here, but if you want a constant volume, you put your sensor down here or down here, and now these will modulate to make sure that pressure doesn't change based upon where the temperature sensor is in the room. So varies flow between cold deck and hot deck to control the room temperature. Velocitrol provides constant flow to the room. Second box is slave to the first box. Supplier is constant volume, variable temperature. So this is a constant volume system. So the room always sees the same amount of air, it just changes the temperature. So this is a way to get zone control down in the spaces. Now, the control system here, now if you, in a system like this, if you wanted a preheat coil, you would have to have another section. You have to put it right here past the filters. So this control section has a return fan starter and a current switch, a supply fan starter and a current switch. Remember, these are constant volume. Has filter system, has economizer dampers, has a chill water coil, hot water coil, and it has valves for those too. And it has a supply air temperature sensor on each deck, and it has a return air supply temperature, and it's a mixed air temperature section. And then, of course, we have controls out in the space. We have temperature sensors out here to the actuator motors on the deal. Now, normally nowadays, we make the cooling valve to be the predominant, the lead box, and we make the hot water slave to the cooling valve. Because we normally have this one tell this one what to do. So the room temperature comes up here and says, I want this to run, so it puts an output to this one, and this one knows it's working in reverse to this one. So this, remember, that's basically the way we work. We'll look at the sequence now. So a typical control sequence for a dual duct unit is a room temperature sensor modulates both a hot deck and cold deck terminal unit damper to provide room temperature. The cold deck box acts as the lead box, and the hot deck box is slave to the cold box. It is kind of what I said there. A typical sequence, the supply and return fan shall run and the outside air damper shall be at minimum position anytime the system is in the occupied mode. Just like the other unit, this economy works the same. Modulate the chill water valve and the hot water valve to maintain the cold deck and hot deck temperatures. Reset the cold deck and hot deck temperature set points based upon the terminal box load or damper position. The cold deck reset range shall be from 52 to 75 degrees, and the hot deck range shall be from 72 to 120 degrees. Energy efficiency is maximized by resetting the hot deck to as close to the return air temperature as possible. So what happens here is the control system watches the damper positions, and if it gets to where many or most of the dampers are getting near full open, then it will drop the cooling set point to make sure these dampers are modulating, but up to 95%. And if one gets full open, it needs to lower it so that space can meet its temperature. If you're on the hot deck side, if the hot deck dampers are modulating to where they're mostly open, just like the cold deck dampers, then they need more heat. Then you raise this hot deck up. Now, the reason we're trying to keep this at return air temperatures, when these first came out, we didn't have all the fancy electronic controls. So the cold deck was set to 55 degrees and the hot deck was set to 120 degrees. And, this system could do fine, but we're reheating all this air for no purpose. So basically, when we started retro-commissioning some of these, we said, look, let's make this temperature set point the same as return air temperature as long as we can. That way we're using the heat of the lights, which used to be substantial. Not anymore, but used to be. Nowadays, it's plug loaded substantial, but we'd use that heat from the return to run this reheat, because we could actually reheat this room temperature. Now these systems can also dehumidify just fine, because this is a reheat coil, and we can do whatever we do with a regular unit. So we don't need a heating coil downstream here. We don't need heating coils here. We can do it here. So anyway, that's why we reset those temperatures. If the outside air temperature is between 40 and 70, and the outside air temperature is 10 degrees below the return air temperature, enter the economizer mode and modulate the outside air relief and return air dampers to maintain the cold deck supply air temperature set point at the mixed air temperature sensor. If the outside air and return air temperature are equal, return to the normal operating mode. So it's just like the other economizer. It's just no different. Just because we have a cold deck and a hot deck makes no difference. So this is exactly like the last unit, where these units modulate together to maintain a room temperature and try to maintain the supply volume the same. So this damper modulates with this one, so that if this is open 50%, this will be open 50% to allow this fan to go out this way. Remember, this is a constant volume fan, so it doesn't change speed. It's constant volume. So you have to set these up so that when this outside air is coming in, you have an equal amount of relief going out, so we don't change the temperature here. And this has to be balanced that way. And this is really a tricky balance condition. And this really proves if your balance guy's really good or not, if you can set that up correctly. Monitor the room temperature, cold deck, hot deck, supply air temperature, supply air return air status. Now, like I said, we could do dehumidification with this if we had humidity sensors down here. But not many of them do that, but you can do that. Right, now here's another one. A multi-zone air handling unit. This is another one that was done prior to having fancy VAV systems. We could do the same thing with this system as we do with a modern VAV system, except the difference is instead of having a one duct run out here with VAV boxes on it, we have zone dampers right here, and we run a duct from this zone damper all the way to the space and to that zone. And then we may have 2, 3, 4, 5, 6, all the way up to 11 or 12 zones off one of these air handling units. Now, back when I was on a designer a long time ago, you get a job that needs 11 zones. Boy, trying to get 11 ducts off this unit was miserable, because these may be 6 or 7 feet tall, and you may have a 4-inch wide duct. So it's a really wide duct, because what happens on this duct is it has a cooling damper and a heating damper on the same shaft. So as the actuator up here rotates this between full open, when this is full open, this is full closed, and when it modulates it, it modulates between the two until you're exactly the opposite. This one's full open and this one's full closed. So that's what's called a multi-zone. It's a 4-pipe. Other than that, this unit here is exactly the same. Now, one thing I didn't mention on the dual duct, you notice this little dash line right here? This is called a blast plate. So when this air is blowing out of this air blower, it's high velocity, and this blast plate is just a plate with a bunch of holes in it, and it's designed to break this up, flow up, forces some air up to the hot water coil and air around this coil, so that this coil isn't impacted with a high jet velocity. And if that happened, we'd have variable flow. We'd have high velocity in the middle of the coil, low velocity at the edge of the coil, which means this coil wouldn't exchange as much heat. So that's what the blast plate is for. It also makes it harder to clean the coil, but that's what it's there. Now, another thing about these is some manufacturers didn't build big enough plenums on either side of these coils so you could access them for proper cleaning. So it's really important that these have access doors in front of and access doors behind, and enough space for a man to get in there to clean these coils. If not, the coils will come completely clogged. So that's important, that the manufactured piece of equipment be big enough to be able to clean these pieces of equipment. So this has a chill water coil and a hot water coil, just like the dual duct, but this is a multi-zone. It has a control system essentially the same. It has starters and sensors, current sensors for status on both the return fan and supply fan. It has a room temperature sensor in each zone. This is a 3-zone system. And then it has 3 damper systems up here and 3 duct systems up here to go to these spaces. It has a hot deck temperature sensor, a cold deck temperature sensor, a mixed air temperature sensor, and a return air temperature sensor to be able to run these. It has modulating valve on the cold deck, modulating valve on the hot deck, and of course economizer actuators. Typical sequence: the supply and return fan shall run and the outside air damper shall be at minimum position anytime the system is in the occupied mode. Modulate the chill water valve and hot water valve to maintain cold deck and hot deck temperature. Reset the cold deck and hot deck temperature set point based on the zone damper position. Cold deck reset range should be 52 to 75, and the hot deck range should be 75 to 120. Energy efficiency is maximized by setting the hot deck temperature to as close to the return air temperature as possible. So it's exactly like the dual duct. So far, the sequence is the same. Room temperature sensors shall modulate the multi-zone damper that mixes the flow from the cold and hot decks to provide the room temperature control. So these sensors here are running this damper, and it mixes the air between these two. So the air in this duct is the correct air to keep that space at correct temperature. If the outside air temperature is between 40 and 70, and the outside air temperature is 10 degrees below the return air temperature, enter economy mode and modulate the outside air relief and return air dampers to maintain the cold deck supply air temperature set point at the mixed air temperature sensor. If the outside air and return air are equal, return to normal operating mode. Now, there's, like I think I said this prior, these temperatures are arbitrary. I mean, I just selected them, but they could be much different. You don't have to have 10 degrees. You could have 4 degrees or 5 degrees. But the one thing we want to do we want to avoid on an economizer is we want to avoid reheat or recooling the air. So if you get these set points way too close, then there'll become a time when you're bringing in air to cool, and you're heating up the air. So you don't want to do that. You want to make sure you don't have that condition. You're overlapping in either space, and you don't want to have the temperature so cold that it is impacting the system. So those have to be set up for the job and exactly what zone you're in and how cold and how warm the temperatures are. So these numbers are somewhat arbitrary. They'll be refined by your specific site. Monitor the room temperature, supply air temperature, supply air and return air fans. Okay, so now we're going to talk about computer room units. They're a constant volume unit. Computer room units are CRAHU, because they also have computer air conditioning units, but these are computer room air handling units. And they're basically a package system. You don't build these up in the field. They cool the computer racks. Nowadays, there's a lot of systems that are actually using in-rack coolers. So they don't have these, but still, these are used very widely. So these air handling units are vertical air handling units, and they suck the air down, return air from the top, but through a filter, through a cooling coil, through a humidifying system, into the blower and into space. They never need a heater. And then they blow this air down the space, and they use an underfloor delivery system, plenum system, to deliver air to the systems. Racks have cold and hot aisles, and I'll show you what that is. As the air is under the floor, and normally these floors depends on how big of a system you have, but they can be from 24 to 36 inches tall. And the reason for that is because they have to be able to move enough air. And so what happens, these are the racks, and these have the servers inside of them. And then, I don't know if you've ever noticed, but the servers have little fans in them that suck air in one side and blow it out the other side. And they're designed to suck all in from one side and blow out all on one side. So when you do this, if you put a perf grill here, it's a floor plate perforated with holes in it, it allows the air from the plenum to enter this aisle. And we call this a cold aisle because we put one set of servers doing this way and one set of servers doing this way. So this aisle and this aisle become the hot aisle, and we don't put any floor grills there. We let this air come in here. So this air might be, I know it used to be they wanted 72 degrees or 65 degrees, really cold. Nowadays, they're letting us get up to 80, 82, 83 degrees here because they found out these new servers can run much hotter. It used to be you had to keep these as cold as possible to make them function correctly, but that's no longer quite the case. So when the air comes out of here, it has all the heat of the servers in it, and then you take it up above and it gets sucked into the top of the unit. Now, the ways I've always liked doing this, a grill right here in the ceiling, lots of free area in the rear. So this heat rises naturally and rises right up to that grill and is sucked into the return air plenum. And then we extended a duct from here up to the return air plenum so we could keep this air from this plenum, blow it in the coil aisle, go through the rack, up to the ceiling, into the ceiling space, and back down to the unit. It made it much better. In the past, they actually kept it all in the room with no return grills, so that this hot air had to move through the room. And we find it much better to partition the area so the hot air is always in a separate space and not into this space. So that's basically the unit. The unit has a control system, of course, and the control system here is integral to the air handler. It is not provided by a third party. Like this, the job may have Johnson controls. This will not be Johnson controls. This will be proprietary controls of whatever the system is. So, if you got a Liebert unit in there, it's going to have Liebert controls inside of it. And all that happens to the control system, if you put a control system in here, is it's just monitoring what it's doing, because the controls itself and providing set points. What room temperature and room humidity do you want? These units come from 5 to 25 ton capacity. Temperature and humidity control, self-contained controls like I just talked about. They run 24/7, and they can be integrated to building controls through a network integration. But these are only right commands these have is room temperature and room humidity. And that's the reason these work really well is if you have 40 of these in a computer room, setting them all the same is a really challenge. So if you have it on a system, you can just set them all the same, and that works really, really well. Because, if one unit is slightly calibrated one way and one unit is slightly calibrated the other, not good. So the maintenance procedures on these basically is calibrating temperature sensors. Okay, available with chill water and DX. So you can get one that's got this chill water coil, but also has a DX coil in it for standby or backup, and then it goes out to it goes out to a condensing system. Okay, the sequence, these is really simple. The supply fan should run anytime the system is enabled. They don't have outside air. The internal unit control panel shall modulate chill water valve and humidifier to maintain room temperature and humidity set points. They never need dehumidification, by the way. It's only humidification. And we humidify computer rooms because of static control. Static electricity is really damaging to solid state components, so they want to keep the static as low as possible. And the way you do that is by keeping your humidity up to 30-35%. The unit shall be integrated into the monitoring system through a network integration. Upon receipt of a unit alarm, the unit shall shut down and an alarm should be sent to operating staff. Monitor the room temperature, humidity, and run hours, so they keep track of the run hours. I didn't mention that these usually have a canister type heater in them, a humidifier in them. They do sometimes have cal rod heaters, which they don't like much because they have too much maintenance. They also can have in here, which I didn't show you, is a water sensor down here in the floor, and it's usually a rope sensor. So you encircle the unit with this little cable, and if it gets a drop of water on it, it will alarm. And what we tried to do is we shut the unit down based upon it. If it's getting water, and the reason we don't want water down here is there's normally tons of cabling down here, and we don't want to put water down in the cabling. Okay, chill beams has been a new concept over the last 10 years or so. And chill beams basically are systems that have a coil in a grill. Basically, it's a grill unit, it has a coil in it that takes cold water, and it has an air supply that goes across the coil and induces room air with the cold air to come through this coil, and basically it cools the room by induction. The secret to the system is the water here is being maintained at 1 degree above dew point, so it can never rain. If you had this water way too cold, it would actually form water droplets on the coil and may drop into space. So this unit is a fan coil unit. Can be a VAV box, but in a constant volume system, it would be a fan coil unit with a cooling coil and a heating coil. Downstream, because this must do dehumidification. So that's a condition there. It has a control system. It normally has 2 control systems. It has one on the fan coil unit, or air handling unit, and it has one down for the chill beams themselves. This unit basically is a fan and 2 coils, 2 valves to run it, outside air damper just like all those. And these have room sensors. And somewhere it must have at least one humidity sensor. And of course, it's got valves down on the boxes themselves, the chill beams themselves. As a little side segue here, these originally were from Europe. Europe actually started with chill ceilings and radiant ceiling panels, and the panels covered the ceiling and to give cooling, and they were just like this. They had this cold water on the back of the panel, but they didn't have air to them. And the problem they had was there was not enough area in the ceiling to provide all the sensible cooling they needed. So they started building these, what they call beams, and they put a square beam in the room with chilled ceiling panels on all four sides. So it ran right through the room like a beam, and it could add to the surface area of the ceiling to get more cooling into the space. And that's where the term chilled beam came into. And then when we started doing chilled ceilings here, we started doing some of this, and we needed more area. So we said, well, what if we put a cooling coil in there? That gave us a whole bunch more area. So we did that, and we put what we called minimum ventilation air across that, because we were using demand ventilation in the space and a displacement ventilation. And so we put it across this coil. We got a lot more surface area. And then they went to induction to induce some of the room air to that. And then these became very popular. But they really run exactly like a chill ceiling. Anyway, that's the chill beam story. So the sequence: the fan coil supply fan shall run and the outside air damper shall be open anytime the system is in the occupied mode. Modulate the chill beam chill water valves to maintain room temperature. The chill beam chill water supply temperature should be controlled to 1 degree above room dew point temperature to prevent condensation. Modulate the fan coil chill water and hot water valve to maintain supply duct temperature set point. Upon fan coil start, the supply air temperature set point should be set to 70 degrees and reset based upon room load. Every 5 minutes, pull the room temperature sensor. If any chill beam chill water valve is more than 95% open and the room is more than 2 degrees above set point, decrease the supply air temperature set point 2 degrees. If the chill beam control valve is above 60% open and any room is more than 2 degrees below set point, increase the supply air temperature set by 1 degree. Reset range shall be from 58 to 85 degrees. If the room humidity rises above 60%, begin dehumidification mode by controlling the fan coil chill water valve to 55 degrees set point as measured at the mixed air leaving temperature sensor. Modulate the chill water valve to maintain a 50% room humidity. Modulate the hot water valve to maintain the supply air temperature set point. If the room humidity drops to 48%, in the dehumidification mode. Monitor the room temperature, room humidity, supply air temperature, and supply air status. Alarm if the room humidity rises above 65%. So basically that's the sequence for them. Sometimes the engineers get a little rolled up on these sequences and become a little bit too complex. And complex enough that it didn't actually ever get installed that way. So this is a new system, the chill beams. That's it for constant volume system. Appreciate you struggling through this with me. Thank you. I appreciate you being a subscriber. I hope you have a great day, and I'll catch you on the next one. Thank you.